topic about fishness. Deliang, please.
Deliang, I think you are muted.
Oh, can you hear me well? Yes.
We can hear you.
Oh, okay, great. Okay, so first I would like to thank you for the organizers for giving me the chance for the participants giving me a chance to talk. Today I'm going to talk about the recent work with Benjamin Volodya, my greatest advisors, and Grenal Ferrand, who is a PhD student of Volodya and Deliang, about the thermodynamic Bethe Ansatz for Fishnet CFTs. To begin with, let me give you a brief review of Fishnet theory in 4 dimensions. Originally, it was obtained as a special limit of n equals 4 super young meals. And for the simplest case, the resulting Lagrangian, the so-called biscalar Lagrangian, consists of 2 complex matrix scalar fields phi1 and phi2. They're NC times NC scalars, and they interact through some phi4 type interaction. Because those matrix fields are because those fields are matrices, the ordering matters. And here, what is peculiar in Fishnet series is that we only have one particular ordering of this interaction relation. That's why this series is chiral and unitary, because we don't have the complex conjugate for this interaction vertex. The Fishnet theory inherits most of its nice properties from its higher dimensional parents, the n equals 4 super young meals. Namely, first, we can prove directly from diagrammatics that the theory is conformal and is robust against quantum correction. Of course, there are some subtleties concerning a double trace counterterms, but they are irrelevant of today's talks. If you're interested, you can refer to these references. And at the planar limit, when NC goes to infinity, this theory is still integrable. For example, it's the integrability of this theory is related to the integrability of the spin chain of conformal symmetry. And if you view this theory as so you study the integrability of the Fishnet theory gives us a way to understand the subset of the Feynman diagrams in the original input form. To summarize, the Fishnet theory is a new kind of 4-dimensional non-supersymmetric integral CFT. And what is nice about them is the Feynman diagram content is much simpler. Okay, now I'm going to talk about how to generalize the Fishnet theory any dimension. Of course, there are 2 ways of generalizing. The first one is to try to perform the same double scaling in other integrable series. However, if you think carefully what are those series, you immediately realize that in higher dimensions, there's only one more candidate, that is the AVGM in 3 dimensions. And indeed, this generalization has made by follow-up papers by Zhong and Omer Volodya. Roughly speaking, it's a lambda phi 6 type scalar series in 3 dimensions with some particular chiral interactions. One side remark is we know based on dimensional analysis, there should be a lambda phi cube type theory in 6 dimensions. But however, so far no one was able to construct any Lagrangian description or find any evidences for that theory in 6 dimensions. Okay, so we have seen the limitations of first generalization. The second way of generalizing is based on the relation with integral SO1, D+1 conformal spin chains. And indeed, one Lagrangian description has proposed by the paper of Volodya and Rico. The idea is to keep the phi4 type chiral interactions and keep the Fishnet coupling chi-square marginal in any dimension. Therefore, accordingly, you have to adjust the dimension of these 2 complex scalar fields, phi1 and phi2. Here, formally, they can write as has some fractional Laplacian. So phi1 has a dimension delta, phi2 has a dimension delta tilde. Using similar technologies as a 4D counterparts, we can find the conformality, and this theory is still integrable. However, there's a crucial difference that for those generalization, we don't know what is a parent series. Like, for example, 4D we know it's obtained from the n equals 4 super young meals. In particular, we don't know this Euler theory has some crossing symmetry to help us to fully fix the S matrix. Therefore, we need to find a new way to develop the integrability machineries. To be more precise, the so-called integrability machinery I'm mentioning is the so-called thermodynamic Bethe Ansatz. It's a set of integral equations that give the exact solution for the simplest set of observables, namely the spectrum of operators. And to run this machinery, one needs to give some input. Those inputs are so-called scattering data, including the dispersion relation and two-body S matrices of the virtual particle called Magnons. I'll explain this in detail later. For technical simplicity, today I'm going to focus on a particular subset of observables in the full series. Namely, I consider scaling dimension operator OJM consists of M phi1 fields and J phi2 fields. Dot means different ways of permuting this phi1 and phi2. Of course, I will assume J is greater than 2 and M is smaller than J. Depending on the values of M, the typical diamond diagrams have different appearances. For example, when M is 0, shown on the left panel, the two-point function of the view type where I put one operator at 0, the other one as very far away. Here, I draw the diagram in real position space, and the black line represents phi2 propagator, and red line represents phi1 propagators. The only diagrams contributes are those real diagrams. For M non-zero, the diagrams look slightly different. They look like some spider web or the so-called spiral diagram. Based on the integrability intuitions, we know the diagram on the left corresponds to the so-called vacuum state, while the operator or diagrams on the right correspond to the excited state. So it's quite natural to start with the simplest vacuum state. So let me recall what happens diagrammatically. The scaling dimension of this operator OM equals 0J start from the classical value and of course receive quantum corrections. What is particular about this operator is that its scaling dimension is protected until wrapping order. For example, diagrammatically, the wave function or domain factor start from 1 and receive contributions starting from the order side to the 2J, and the next order is order side to the 4J and so on. Suppose we find a way to resum, and you can read out the enormous dimension from diagrams using the standard RG methods. But due to the simplicity of this diagram, there exists an alternative operatorial approach of computing them. Namely, the so-called those Feynman diagrams can be seen as some repeated action of some integral operators, the so-called graph fitting operator. Let me show an example here. I consider operator J equal to 6 case, and I consider diagrams as 2 wheels. I claim that this diagram is equivalent to the trace of certain operator denoted here by gamma equals 2 to the power 6. I will explain the details about the operator, but suppose this equation is true. Computing this diagram now is equivalent to finding the eigensystem diagonalizing operator, read out its eigenvalue and perform the completeness relation. Here for the n equals 2 case, let me explain what is this operator is. It consists of a portion of this diagram. It consists of this black propagator and the red propagators. For example, in the radial direction, it has a fixed point x0. It's a position of the initial operator, and those operators are connected by the black propagators of dimension delta tilde. On the other hand, the horizontal direction, we have these 2 red propagators with scaling dimension delta, and the integral kernel depends on 2 sets parameters, x and y. The action of this integral operator is defined by integrating over a second set of variables. For example, when I say gamma square, it's defined by integrating the y of the first operator against the x of the second one. Diagrammatically looks like this. So you immediately see by definition, this lambda to 6 is equivalent to this diagram. And then by identifying the endpoints, we can recover the Feynman diagram just by definition. Okay, so far so good. We know there exists an alternative way, and computing Feynman diagrams is equivalent to finding the eigensystem and study the completeness relation and the eigenvalues of that operator. Now, suppose we can do that. The next task is to try to find the field theory, try to find the dictionary from field theory to integrability. Here, in integrability, the phi 1 excitations are, for example, here in this diagram, the red lines are phi 1 properties. We see it as a trajectory, some virtual cortical called Magnons propagating along the vacuum consists of this black line. And to make the actual dilatation operator manifest, it's the standard to decompose the d-dimensional Euclidean space to a spherical coordinates and map the plane to the cylinder. Basically, in the what follows, we'll parameterize the distance by the coordinate sigma, and each point, because of the sphere, has all these symmetry. Now, since we view those red lines as trajectories, we are basically view the radial direction as the space of this Magnon, while on the other hand, we view the angular direction as a time direction of this virtual particle Magnon. Therefore, the time evolution of those virtual particles are generated by the repeated action of this graph building operator. So to compare with the standard CFT approach, usually in radial quantization, we treat the radial direction as the time, the angular as space. So that's here we swap the role of space and time. So that's why it's usually called the meter channel. In this channel, the Magnon scattering data is fully determined by the eigensystem of the graph building operator. For example, the dispersions are determined by gamma n equals 1. In particular, for example, the energy by definition is a weight of the Magnon conjugate to the time variable is related to the eigenvalue of this gamma operator. And the n-body wave function of a scattered Magnon is related to the eigenfunctions of the gamma n. We are also interested in the two-body S matrix. By definition, it's a relative phase of two Magnon scattering when the two Magnons are far apart. And the general expectation is the wave function is that asymptotic limit factorized into two terms. So first term, the plane wave with some tensor function C controlling the OD degrees freedom coming from the spherical decomposition. The second term looks quite similar to the first, but the role of P1 and P2 are swapped. And the tensor function C is acted with some non-trivial tensor function S, depending on the spin of these two scatter particle L1, L2, and the rapidity U1, U2. And assuming integrability, those data fully, of course, determine the spectrum because higher S matrix factorizes two-body S matrix. So now we understand we have to diagonalize this graph fitting operator. Let's start with a gamma n equals n. In that case, the eigensystem was quite simple to obtain. The reason is the gamma n equals n, although it cannot be fully conformal, it still commutes with dilatation and rotation around the fixed point x0. Therefore, the eigenvector must take the form of the pure power-like times some tensor bar controlling OD degrees freedom. And the natural candidate for this OD degrees freedom is the rank L symmetric traceless tensor. For example, you can take for a complete basis, you can take to be spherical harmonics. Once we fix this tensor power, we can make a choice of this power beta tilde to find a complete orthonormal basis. The choice we made is as follows. It has a fixed real part d minus delta over 2, and its imaginary part is parameterized by some real number u. Now, with this eigenvector, it's quite easy to read out the eigenvalue. The eigenvalue looks as follows. I don't have this eigenvalue depends on the L. L's rank of the symmetric traceless tensor, and physically is the spin of this Magnon. From this, we can directly work out this dispersion relation. For example, the Magnon momentum P by definition is variable conjugate to radial distance log theta sigma definition log x. So e to the I, from here we know it's e to the I 2 log x. So P is 2u, and P is constant, doesn't depend on spin L. On the other hand, the weight of time evolution by definition e to the minus epsilon L, and is equivalent to the eigenvalue. Therefore, we can read out the Magnon energy as minus log lambda L. Now comes the more interesting part of the Magnon S matrix. Before presenting the general construction, let's first talk about what do we expect from this S matrix. For example, we know the S matrix depends on the rapidities of the two scattered particles and their integer spin of these two particles. First, because assuming integrability, the matrix part of this S matrix is fully determined by Yang-Baxter, because they are ODE tensors. They are fully this was known a long time ago. And secondly, as the eigenvector, if we find the eigenvector, the eigenvalue of the n equals 2 must factorize to the product of two the n equals to 1 eigenvalue. Physically means the total energy, the sum of individual energies. Now, for example, we managed to find the eigenvector. It's quite complicated. I don't have to fully explain how to construct. The basic idea is the following. First, this consists of some, it's a propagator where xa and xb are some points of integration. It consists of two pieces. The first piece only depends on the rapidity of the first particle, while the last leg only depends on the spin and rapidity of the second particle. And the idea is to, by making some particular choice of the weights of the propagator, and we apply some special differential operator here. C is a symmetric stressless tensor separately in first L1 indices and last L2 indices, acting on the two external points x0 and x0 prime. After differentiation, you take x0 prime to be x0, to be, of course, the position of the initial operator. Then we managed to prove this is an eigenvector. So once we are able to find the eigenvector, then we can try to find the asymptotics from that eigenvector. Indeed, when two magnons are far apart, the asymptotics takes the expected form. And the S matrix has the following form. First, it consists of some tensor part, which is the solution of the R matrix, was determined by Yang-Baxter relation. More interestingly, it has some scalar part. The structures as follows. First, we have the scalar function Pascal S, depending on the spin of two particles and the rapidity difference. Only depends on rapidity difference. Secondly, it also has a part that depends only on the spin or rapidity of the individual particles. This function is called by F. The expression for Pascal S and F are given as follows. I don't have good explanation of why this is the case, but that's what we found. Of course, in general, the S matrix is quite huge matrix. We are unable to read out the full term, but we are quite confident of our result for the following reason. Because for spin L equals to L prime equals to 1, we are able to reproduce the full S matrix, including the matrix part. Of course, we know by symmetry it consists of triple identity permutation and trace. This was found by the Molotov brothers in 1997. And second, this R11, as we know, is a building block for higher S matrix, higher R matrix. So in principle, fixing R11 is equivalent to fix all higher R matrices. So what remains to be determined is finding the scalar prefactors. And to do that, we are able, the idea is to project this wave function into some simple subsector. For example, we project to a wave function that is fully symmetric in all its indices. In that case, in this normalization, the eigenvalue of this R matrices trivializes to 1. And in that case, we can indeed reproduce a scalar phase. Of course, if you take D equals 4 and take the canonical value of delta, we can reproduce the result from obtained from deforming the n equals 4 Deliang mills. Okay, once we obtain the scattering data, we can run the TBA. And for people who are not very familiar with, let me recall the picture. TBA equation is as follows. So the scaling dimensional operators map to the free energy of the magnons, and the length of operators map to the inverse temperature of the free energy. And the coupling Fishnet constant is equals maps to the chemical potential of this. And with all those inputs, the scaling dimension is equal to a classical part minus the infinite sum or quantum correction. Here, the sum is over integer integers, the physical meaning of that is the spin L contribution of this spin L contribution to the scaling dimension. And each integral is determined by some function, a special function called y function, y1L. The just the infinite system of nonlinear equation determine the.
Deliang, can you
Sorry?
repeat?
Previous one, yes. This one, or can you hear me well now?
Now we can hear you. Can you repeat, like, starting word from equation for delta?
This one? Yes.
Yeah.
Sorry. I mean, the scaling dimension delta is equal to the classical part minus the infinite sum over integers of some integral. The physical physical meaning of the L is the spin L contribution to the scaling dimension, and each of the integrals is determined by a special function called y function. The physical meaning of that is it characterizes the distribution energy of the spin L Magnon. All right, so the TBA equation are quite standard, but so how much time do I have, Dima? So
you started later, like still 7 minutes, yes, I would say.
Okay, that's great. So first is the equation governing those y functions that enters the energies. For example, those y functions can feel the presence of the dispersion. They can feel the presence of the chemical potential, and among them, they interact through some logarithmic derivative of the potential. Moreover, in order to diagonalize the matrix degrees of freedom, we had to introduce a set of functions called auxiliary y functions, and the interaction of those y1 functions with the auxiliary y functions is through the rational kernel. This is just the fused x-axis kernels, if you want the terminology. Of course, the second set of auxiliary y functions are quite standard. For example, for those y functions, they can interact with their neighbors on the same Deliang diagram through the same rational kernel. They can also interact all nodes on the same position of the same Deliang diagram can interact with their neighbors by some shifted kernel, but that's quite standard. I forgot to mention, for simplicity, I only consider TBA for the d-even case, but in principle, you can consider all cases. Yes. So far, the TBA equations look quite complicated, but nicely they can be recasted into the standard universal function. For example, all y functions except the first one can be recasted to the standard universal y system form, which was first proposed by Balog. Here, the plus means the shifting the argument of the corresponding y function by L2 minus L. What is more interesting is the equation governing the first node. It looks quite complicated and reflects some asymmetry on this drawing, because this node is fully determined by all nodes on the second layer, all nodes on the second layer. Here, the upper index k means the shifting arguments by IK2. Of course, our system is also gives us some particular asymptotics. For example, when the argument u is large, the y functions on those y functions on the first row becomes very massive and divergent, like log u square. And the driving term is nothing but the exact scaling dimension. On the other hand, all auxiliary y function in that limit goes to a constant. By constant, I mean the constant solution of the decoupled, basically a character solution of the reduced Deliang diagrams. Okay, so far I explained how to do the ground state, but the natural question is how to generalize the framework to excited state. In the integrability framework, this can be done quite easily because we know there's the famous contour deformation rate. The idea is if you have the excited state, the log 1 plus y will have some singularities. So we have to deform the contour accordingly to avoid the singularity, or effectively we have to pick the residue of deformed contour and pick residues over this a special point. And once you can do that, the TBA equation most of the TBA equations stay the same, except for those including function y1l. They pick some additional driving term. For example, here here is a enormous dimension of the gamma n. It now has the leading part. It now depends not only on the infinite sum of y function, but also on the finite sum of the special points. Okay, so far so good, but we developed good machinery. In principle, it can give us spectrum. But it would be nice if we could reproduce or at least verify whether this deformation trick is correct, or can we reproduce some results from the diagrammatics. The simplest way to do that is to go to asymptotic limit. The meaning of because in that limit, all the diagram contributes start from the leading order. For example, by definition, asymptotic limit is when the operator length is very large. We consider a weak coupling limit. In that limit, all y functions decouple except for the first y1l equal to 0. So the TBA equation reduced to the ABA equation as follows. What is nice because all particles are just scalars in this case. So the complicated S matrix becomes just some number. So it's an algebraic equation. Once you solve this algebraic equation, you plug in the formula of enormous dimension, you obtain the enormous dimension. Because those operators are single trace, we had to supplement this ABA equation by the cyclicity condition as well. Yes. By the way, I have to recall the meaning of asymptotics. The meaning of this asymptotics is the solution of this ABA equation is valid up to the wrapping order psi to 2j. So you see the larger j is the better result we can have from this simple algebraic equation. And what is nice is this result from ABA matches direct diagrammatic computation up to 3 loops. For example, I show you an example for j equals 4 and equals 2. There are 3 different ways to distributing this phi1 operator along the phi 2s. And here I show you the mixing matrix of the 3 operators up to order xi to the 8, 4 loops. Sorry, yeah. And after some struggling, I managed to compute all this Feynman diagram to us. Then once I obtain this diagrammatics, I can diagonalize the mixed matrix to find the eigenvalue. That is the enormous dimension of the 3 operators. However, on the ABA side, it's quite easy because it's algebraic equation. We just need to extend all beta roots around their canonical value. So we applying back the solution, we immediately find those eigenvalues and they agree perfectly. So it's a non-trivial check for the correctness of our ABA equations. Now I can summarize. The summary is quite simple because we find TBA equations for OJM consists of M phi 1 and J phi 2 for conformal Fishnet series any dimension. In particular, we're able to derive the Magnon dispersion relation and two-body S matrix directly from the Feynman graph. The strategy is to find the eigensystem, the graph building operator for n equals 1 and n equals 2 case, and find the asymptotics in the n equals 2 case. There's one point I'm unable to talk is the dual TBA that relates to d-dimensional graphs to the sigma model. That generalized work of Benjamin I in the previous paper. Okay, some outlooks. The first one is about the TBA for other types of operators. For example, so the operator with spinning operators with derivatives. That was in principle doable from the contour deformation. But the second set of operators are more interesting, but that's the most general operator in the conformal Fishnet theory. But so far we don't know how to incorporate it in our framework. And there are some algebra. The second direction is a reformulation of TBA, like finding the Baxter equation or quantum spectral curve for this infinite TBA system. For example, our recent work of Grinnell, Rubin, and Volodya, where you can refer to. Today, I'm also going to talk about the computing two-point function. Of course, one can also pursuing to evaluating high-point function. There are a lot of progress, but there are still many interesting directions. The next step is to find a SOA approach to non-compact spin chains of SO and D+1 in the principal series representation. For example, we now find a way to generalize our construction to arbitrary ends. In 4-dimensional flow, Sergey and Enrico has their construction. It would be nice to uniform them and to give those will give some hint to the full SOA approach to this non-compact spin. The last thing is about the holographic dual. For example, in 4D, we found the work of Amit and Collier, we know the Fishnet, but what is the holographic dual for the D-dimensional cases? Since I have 1 minute left, let me give you a second outlook on the recent work with work in progress with Benjamin, Lance, David, and Alex.
No, it was not until 7 minutes. It was 7 minutes left. So, I mean, just very shortly.
Sure.
Just do it very shortly.
Sure. Okay. I mean, the Benjamin and the Lance would find a representation for this 4-point functions. And in this work, we are able to prove the equivalence and more interested in finding the solution in some dynamic limit when the size goes to infinity, but this ratio of these two sides keeps fixed. What we find is the free energy per side now depends on the ratio, and it's all greater than homological. So it will be interesting to understand the physics behind this. Okay, so thank you very much for listening.
Thank you, Deliang. Okay, so we have 3 minutes for questions. Julius?
No, I was just clapping. That's all.
Oh, it was clapping. Actually, I do not see raised hands so far. So
nice talk, Deliang. Maybe I can quickly ask, since you were pressured for time, maybe you could spend another minute on the outlook that you had on the limit, this particular limit of fishnets. Yes.
This one, right? Or yes, yes. Yes. I mean, this 4-point function, based on integrability, we know we have two equivalent integral representation, one BMA integral from hexagon and the flux tube integral from the flux tube approach. And if you combine these two integral, look quite similarly different integral approaches, and using the Steinman relations, Benjamin and Lance were able to find a closed formula, all-loop formula for that closed representation for this 4-point as a ladder determinant. So a natural expectation of the thermodynamic limit of the lie diagram is that because the bulk is also of the Fishnet type, so the bulk free energy goes back to the result of Zamalot curve. However, in this thermodynamic limit, we find that the free energy per side, I mean, in the log or partition function divided by m times n, it's a function of the k, and it's always greater than Zamalot curve result. We checked this expression. The physical interpretations of that. Yeah.
Okay, so thank you, Deliang. So let's send Deliang again.
Yeah, thank you. Yeah, I should stop screen sharing now.